Okay, so let's continue on. So currently, as we mentioned in the earlier video, this over here is actually 3.5 cm. So remember the second step, what we want to do, right, is to see which part does this vernier scale lie on. So this vernier scale lies in between 3.6 or 3.7. And then the second step we want to do is to actually find out which line aligns with each other. And this is actually the line that aligns. And if you count 1, 2, 3, 4, 5, and 6, you can safely conclude that the reading in this situation will be 3.66 cm. Okay, part C, I want you guys to just try doing it. You can just pause the video. Okay, so now let's again go through the first, second, and third step. So the first step is to identify which 2 points does your zero line on your vernier scale lie. So in this situation, it lies in between 8.2 and 8.3, and obviously you just pick the lower one. So now we know the first two digits. The second step is to basically find out the one that aligns, and clearly you can see it's this one over here. And the third step is to basically count. So this is 1, 2, 3, 4, 5, 6, 7, 8. So this means the second reading is 8. So from here, you can know that this reading here is 8.28 cm. Okay, this part should be relatively simple to understand. Now, moving on to work example 2. Work example 2 will be slightly harder because it actually involves your zero errors. So remember earlier in the previous video, zero error is basically defined as the error where your vernier scale and your main scale is not aligned, which you can see clearly over here. So zero errors, there's actually two types. There's positive zero error, and there's also your negative zero error. And a quick recap, remember that your positive zero error basically means that your vernier scale in this situation is it is after your main scale. And your negative zero error basically means that your vernier scale is before your main scale. So in this situation in diagram A is actually an example of your positive zero error. Okay, so now to measure the positive zero error, what we have to do is to just read it like a normal vernier caliper. So in this situation, it lies in between 0 and 0.1. So it means it is 0.0 something. So the something is basically the one that aligns over here, which is this line, as you can see, and it is 1, 2, 3, 4. So your zero error is 0.04. But remember, this is actually a key thing that you have to remember. Your zero errors, whether it's negative or positive, even though if it's positive, you will still need to write your signs to show that this is a zero error. And as always, remember to always include your units. I cannot emphasize this enough. For zero errors, even though your answer is a positive zero error, you will still have to include your positive sign. Okay, so now for diagram B, we can just read it like a normal vernier clipper, again, through the same three-step process. First step, identify your zero mark. Zero mark is somewhere in between 5.2 and 5.3, so it means that the first two digits will be 5.2 something. And to determine the last digit, what we want to do, right, is to first look at the line that aligns with each other. And if we start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, we can see that our second digit here is 9. So from diagram B, using the faulty vernier caliper with a positive zero error, we get the reading 5.29. So take note that this 5.29 cm, right, is actually the reading with the zero error. So what we want to do now, right, is to actually determine what is the actual measurement. So to find out the actual measurement, what you want to do, right? So this one is basically the incorrect reading. So the actual measurement, aka the correct reading, is actually simply your incorrect reading minus your zero error. So in this situation, we found in diagram B that our incorrect reading is actually 5.29 cm. And we found out that our zero error over here that we found out earlier, it is 0.04 cm. And when we deduct them, we will get the answer 5.25 cm. So this 5.25 cm, right, is actually the actual measurement of your wooden block. Okay, so now let's look at another example. So this example, in this situation, because your vernier scale is actually in front of your zero mark over here, this is obviously a case of a negative zero error. So negative zero errors are slightly tougher because there's an additional step that you have to do. So again, you want to read this. First step, obviously you can't identify what it is because it is not in between any two lines on your main scale. So instead, for your negative zero error, the first step is just to find out your line that aligns with each other. And in this situation, the line that aligns each other for this specifically is this line here. However, take note, this is an important part. Instead of counting from the zero mark, 1, 2, 3, 4, 5, 6, what we want to do for your negative zero errors, remember negative zero error only, we will have to count from the 10th mark instead. So this will be 1, 2, 3, and 4. Always remember negative zero error, you have to start counting from the 10th mark. So in this situation, your zero error is actually 0.04. And as always, remember for zero errors, we have to include our signs, whether it's positive or negative. In this situation, it's a negative zero error. And as always, include your units. So it's negative 0.04 cm. Then for your diagram B over here, diagram B, we have to first identify, this is just your normal vernier caliper reading. So the first thing you want to do is to basically identify where your vernier scale is. So your vernier scale in this situation is in between 1.7 and 1.8 cm. So in this situation, we have found out the first two digits. The first digit is actually 1.7. Then the second step we want to do is to basically find the line that aligns, which is this line in this situation. And we count 1, 2, 3, 4, 5, 6, 7, 8. So this means that your second one over here is 8. So the incorrect reading over here is actually 1.78 cm. So now the question is asking for the corrected reading. So remember earlier, the previous question, we said that our corrected reading is equals to the incorrect reading minus the zero error. So we will have to use this again. So your incorrect reading in this situation is 1.78 cm. And take note, our zero error in this situation is negative. It is negative 0.04. So what we want to do, right, is to also include a bracket because this is a negative number. So bracket negative 0.04. And if you key this into your calculator, your answer will be 1.82 cm. Take note, in this situation, because your zero error is a negative error, when we are substituting it, we must always include a bracket, and negative becomes positive. So in this situation, the corrected zero error will be 1.82 cm. Okay, now let's go on to period. So for this topic, period is actually quite an interesting part. So the first thing you have to know is that your period is actually related to your time. So the SI unit for time is actually in seconds. Take note that SI unit is seconds and not hours. Okay, so the first thing we have to do is to be familiar with the definition of a period. And a period definition is the time taken for a pendulum to complete one oscillation. So one oscillation is basically your ball over here moving to the right and then moving to the left. So this is actually one complete oscillation. Okay, so this is an experiment that you can set up to actually determine the period of a pendulum. But take note, this you should be familiar by now. Your period of a pendulum is only affected by one thing, and the thing is actually your length. Period is only affected by the length of the string. It doesn't matter if your mass is heavier or you're on a different planet, it is only affected by the length of the pendulum. Okay, so take note, when we are actually finding out the period of something using an experiment, what we want to do, right, is to actually use 20 oscillations instead of one oscillation. And let me tell you the reason why. So let's look at the human reaction time. The human reaction time is around 0.03 seconds. But to make life simple, let's just say, for example, our human reaction time is 1 second. So if we use one oscillation in this situation and we want to measure it, let's say the one oscillation takes 4 seconds. So as a percentage error basically can be defined as our human error or error in general divided by the total time of the experiment. And in this situation, our percentage error will be 1 over 4, which is 25%. So in this situation, if we took 20 oscillations instead, if we have 20 oscillations, the total time for this is actually 80 seconds. And let's calculate the new percentage error. The new percentage error in this situation will be 1 over 80 times 100. And as you can see over here, it is around 1 point something percent, probably around 1.3%. And as you can see over here, the percentage error significantly reduces. So this is the reason why we want to use 20 oscillations instead of one oscillation. So if we actually found out what the time taken for 20 oscillations, let's say if I told you that 40 seconds is required for 20 oscillations, To find out the period is actually a simple mathematical equation. We can simply take 40 seconds divided by 20 seconds, which gives us the answer 2 seconds. So always remember when you're setting up an experiment or when the question is asking you what is the reason why you need to have 20 oscillations, this is the explanation. So you can reduce the percentage error in the experiment. Okay, so that's basically your chapter one over here. And I'll be moving on to chapter two, kinematics, soon. Thanks for listening.